Hello everyone. In this video, we're gonna learn how to make the control for formation preservation in multi-robot system. I am Arpit Joon, and this work is done with Dr. Wojciech Kowalczyk. One day, he had the idea that how we can preserve the formation in multi-robot system. So, in simple words, I could tell that when a new robot wanted to join the formation, the other robots which are already at their desired position, it should not get disturbed. So, a robot should quietly or nicely join the formation. And now we can directly jump into the presentation and we can see how it could be done. And here, this is the exact title of our work, Formation Preservation Control for Multi-Robot System using Artificial Potential Function for Collision Avoidance. So in our controller, we will going to use these artificial potential functions to avoid the collision in the environment. Okay, these are the topic which we will going to cover in this video. The first one is the motivation, that what are the advantages of the APF, why we are even using the APF, and the problem behind this APF. And the third one is like how we are modeling our robot and what are the functions which we're gonna use in the artificial potential functions. And in this video, maybe I will be going to just say APF. So APF will be the for artificial potential function and our proposed control law, that how we are calculating the velocities and its stability analysis. However, we will not going to talk in detail about this, but we will just look the on the important equations, and we will also see the simulation video. We will also see the simulation results, and then we can conclude this video, and finally you will get to know that how you can make the control for formation preservation. Okay, let's move ahead. And this slide will going to tell you what are the advantages of APF. The first one, they are simple and analytical to use. So what it means that each robot doesn't need a high computation power to calculate. They just need the location of themselves and the location of the other robot or the location of the obstacles in the environment to avoid them. This is the very first point. And second point, they are suitable for decentralized implementation. So it means that we doesn't need a centralized system or a high computing system to calculate everything, to calculate for n number of robots in the environment. Just each robot could have its own local APF calculation. Okay, the third one, they are effective for real-time collision avoidance. So it means the robot doesn't need the prior knowledge of the environment. When an obstacle or when another robot will going to come in front of it in real time, then they just can avoid them. And the fourth one, they are easy to compile with the navigation information control systems or the control approaches or control algorithms. And we can see the application. So they are used in mobile robot navigation, swarm coordination, leader follow configuration, multi-agent formation control, and they are also used heavily in obstacle avoidance. These are the main advantages or the application which I have shown, but there could be n number of application or n number of advantages. Now, if these proposed algorithm or the APF have the advantages, then it also have some disadvantages. So now we will talk about the disadvantage by this example. So if we want that these four robots should make a square in the environment, this should be the final formation. So in the initially, this robot is far and each robot have its APF around it. So when this robot will going to come at this desired position, these robots which are already at their desired position, they already have this active APF. And when this robot will going to come near or close to these robots, the active APF will going to generate the repulsive forces into them, and this will going to disturb this formation. So these robot could displace from its desired position as new robot is going to join it. And this is the problem. We have seen this problem with 4 robots, but what about the n number of robots? For example, like if we have 100 or 200 or 300 robots in the environment, and this could be a disaster, total disaster. So it could be a chain reaction. So one robot will going to disturb another robot, and another robot will going to disturb another. And this will maybe never ending. Okay, but so we can conclude that the main problem is the unnecessary displacement of the settled robot. So if a robot already reaches this, you can say desired target, it should not move. It should just stay there. For an example, if you are going into your classroom and you are taking a lecture, so you're gonna sit on one place, and when a new student or another student will going to join the lecture, it will just take a different place and sit. So you don't have to always move for each and every student, and that's the idea, you can say, behind it. And the second one is the deformation of the desired formation. Of course, the formation will going to deform. And the third one is the problem is the controller have to put extra effort to bring those robots back to their desired position, because in the starting they have already at their desired position, but a new robot is coming and it's gonna disturb the whole formation. Then the controller have to put again back the whole effort to bring them back. So this is the extra work the controller have to do, and of course there will be more loss of the energy while doing it. Okay, and finally we can say that it is leading to reduced formation stiffness. So the formation is not rigid. So, and these are the problems which our proposed controller is solving it. Okay, now we can move forward. And here this h derivative is equal to the u. U is the vector for the control inputs in the x-axis and in the y-axis. And this h is equals to x and y. X and y is not the center point. Remember that. But actually, it's the hand position or the control point of the robot. I is the ith robot, means like there could be n number of robots, and this could be like for the first, for the second, or for the third robot. So that's why these are having I. Okay, so if you have a holonomic type of robot, means the robot have mechanism wheels all around it configuration, or all around its motor, then this ux and uy could be directly given to the robot. And if you have a non-holonomic robot, means a differential drive robot, means a robot have just a left wheel, a right wheel, drive system, and some caster wheels, then you have to do partial feedback linearization to get the linear velocity and the angular velocity from the ux and the uy generated from the controller. Okay, now in our case we have used the differential drive robots, and for this we have to choose the hand position. So this is the robot center. The robot center could be presented by xc and the yc, and the theta is the robot orientation. So xc, yc, and theta c is the pose of the robot, and this linear velocity and the angular velocity. So v is the linear velocity and the omega is the angular velocity, and this hand position is just a virtual position, a virtual, you can say a virtual point. This doesn't exist in reality. It is just a virtual point, and the distance from the center point and the hand position should be the capital L, which is positive distance. So it should be greater than 0. And another thing which you should remember, that this hand position should be on the x-axis of the robot. This is the center point. This is the x-axis. The y-axis is going from the motor drive, and this hand position should be at a capital L positive distance from the center points towards this x-axis. Okay, Now we will see the main final equation responsible uh, to calculate the linear velocity and the angular velocity. So after putting all these values, we will get the linear velocity and the angular velocity. L is already known because it's a constant, and theta c is the orientation of the robot, and the ux and the uy is the input velocity in the x-axis and in the y-axis, and theta c is the orientation of the robot. Okay, and the ux and the uy will be calculated from the controller, and we will see in the further slide that how we have calculated the ux and the uy, and this linear velocity and the angular velocity will be directly sent to the robot, and L is a positive constant. Okay, so in our environment, each robot is surrounded by the APF. Now the APF are artificial potential functions, and uh, they are a virtual circle. It's not a real circle, but for example, if a robot is there, we're gonna make a virtual circle with a smaller r, which we say the robot collision radius, and the capital R, and the capital R should be greater than the smaller r, and this region is the collision avoidance zone. So when another robot is going to come into this region, this robot will going to have this repulsive forces on the opposite direction, and that's how the robot can avoid collision from each other, or robot can avoid collision from the obstacles. Okay, so we will talk about the two type of robot platform. So first one is like for the holonomic type of robot. So as I have already discussed, the control point for the holonomic could be the center point of this APF, and this hand position or the control position should be the center point also for the APF. Okay, so here for the holonomic, the center point is the control point, and the center point for the APF is also the center point here, this center of the robot. Now when we will going to see the differential drive robot, our control point is the hand position, which is here, which is not the center point. So the center point of APF is also the hand position. Okay, and you should take the smaller r such that it should cover the whole robot. Okay, and here I would like to mention the L is the distance between the pair of the robots, and L is just the Euclidean distance between the robots in the environment. Now this B present represent our function, represent our potential function, and that's how it gonna behave. So when another robot is at just the border, it will going to give you the value 0, but when it is close to the another, you can say, border of this robot, it gonna repel with the very force, which a very huge force, and we can say it's like the 1. So is the value is from 0 to 1, so 0 at the boundary, and it's more strong repulsive force when it is close to the boundary here, which is close to the border of the robot here, or we can say close to the robot. And this is only you can say calculating this repulsive forces when it is in R and the capital R. So when the another robot is between this region, smaller r and the capital R, then only we are going to calculate this repulsive forces. So in this, L you already know from this equation, and the smaller r and the capital R are this. So you know the every value, and exp is the exponential. Okay, so this function will going to give you the value from 0 to 1, but we have to scale this value from 0 to infinity. That's why we are using the scaling function, and this b is putting the value here and in the numerator, and in the denominator it is 1 minus b function. Okay, so finally you will get the value from 0 to infinity. Now let's talk about the controller. This u vector have the velocity ux and the uy into this u. Okay, the k is a positive constant, and the capital E have the smaller e minus zeta multiplied by the artificial potential function. These are the values generated from the artificial potential function, but this is the partial derivation. Remember that. Okay, The smaller e is the xd and the yd. Xd and yd are the target point of the robot where it should reach. And this is a set point controller. So when you are going to start your simulation or when you are going to do your experiment, these will going to remain fixed. Only in the deadlock situation you have to change those xd and the yd, and x and y is the current position of the control point of the robot. Okay, this zeta is equal to the e norm vector here. This is the e vector and this is the nominal of this, or you can say the absolute value of this vector, and we are putting it here multiplying with the APF. So what happens when a robot is already going to reach its desired position? The error will going to become 0, and finally this zeta will be 0, and the whatever the values coming from the APF will be 0. So it is working like a switch. So when a robot will going to reach its desired position, the APF will be inactive at that point. So that's how our proposed algorithm work. And there is an assumption which you should remember, that the distance between the reference position remains greater than the APF interaction range. So the collision avoidance interaction becomes inactive when the robots converges to their target position. However, for like showing this assumption, I will go back to the previous slide, and this is the perfect example. So if in our environment, if there are just two robots like this, so you should make the desired position so that when they will going to reach their desired position, the distance between the robots should be greater than the r. So you can say that this is a perfect example of our assumption. So these two robots have followed our assumption. Okay, now this is for the stability analysis. I am not going to talk in details, but this is the Lyapunov function and it is fulfilling these conditions. And finally, I would like to show the final equation here. So this is less than and equal to 0. What it means that it is stable in the sense of Lyapunov. Okay, and what about the singularities? What about the local minima? So when the two robots will going to stuck in the deadlock situation, we can change the desired position for a set of temporary time, maybe for few seconds. So we can change their desired position so they can come out from the deadlock, and when as they will come out from the deadlock situation, we can put again the initial position, again desired position where the robot should reach when the simulation or when the experiment have started. And that's how we're going to resolve the deadlock situation. Okay, so finally we can go to this slide and we can see the parameters of the simulation. So the k was chosen 0.12, of course it's positive. The smaller r 0.3, so it is surrounding the whole robot completely, and the r, capital R, is 0.7. So this is the radius, so it means each robot is surrounded by a 1.4 meter. Okay, the hand position is 0.1, so 10 centimeter away from the center point. And the number of robot in our simulation, we took 9 robots, so that's why capital N is 9. And we have also compared our results with the classical APF, and for the classical APF we have chosen our zeta equals to 1, and this our proposed zeta, which you have already seen. So this is the comparison which you're gonna see in the simulation video and also in the plots. Now the most interesting part, we can see the simulation video. I will just open. Okay, I will start it. Okay, so this is for the experiment 1 when zeta equals to 1, and this robot is at is here. This is the initial point for this robot, but final point for this robot is this point. So this robot should reach this robot, and these remaining 8 robots are already at their desired position. So let's see what happens when with the traditional APF. So you could see when this robot was wanted to go at this position, so this robot is disturbing the other robots in the formation. And this is not a good thing, because now the controller have to put extra control effort to bring those robots back to their position. And that is the disadvantage or the limitation with the traditional APF. But we are solving this problem with our proposed solution. So the next scenario is with our proposed zeta, and in that you could see the results. So I will just skip it, and here I would like to mention that this robot was started at the same initial point as in the previous scenario. So the parameters and the whole environment condition is exactly the same. So here you could see that when this robot wanted to go here, now these robots are not moving from their position. So this formation is rigid. So these robots are not getting deformed. They are not in unnecessary movement. And that's how we are also saving the huge energy. However, we have not shown any comparison of the energy, but that's what we can look. So, but maybe in the future we will introduce some mathematical model to prove that we are saving the energy. And now you can see that these robots are already at their position, and this robot have reached its position, and it was going from in between the robots. Okay, now we can come back again to our slide here. Oops. Okay, now this is the plot. This is a simulation plot here. This is a simulation plot. You could see the robot have started from this and even from this, so it was the same. But when this robot was uh, going to its desired position, it have disturbed the whole formation. So you can see these robots have moved from their desired position and it was disturbed, and then the controller tried to put efforts and bring them to their desired position, but it is extra work. So why to do the extra work? Here in this scenario the robot have started, but these robots which were already at their desired position were not displaced, and that's the benefit of using our proposed algorithm. Of course, our proposed algorithm is very good and everyone should use our proposed algorithm. Okay, now here this is a position error in the x-axis. So you can see the error was generated for the three axes, and here it is just for one robot. Why? Because in this scenario, the two robots, actually the three robots were moving. This robot and the two robots got displaced, and here in this scenario, only one robot was moving. So the error was only for the one robot, and here you can see the error for the three robot. But you can also observe that the errors are converging to zero. So what it means that they are going to their desired position. And this is the error in the y-axis, and this is the control input in the x-axis, and the control input in the y-axis. Here you can see that the controller have to put more effort for the other robot so that they can also come back to their desired position. Okay, and this is the plot uh, for the distance between the pair of the robots in the environment, and this dash line and this dash line, it represents the smaller r and the capital R, and this is the APF region, and both the plots shows that they were in the APF, but in our proposed zeta, it's not disturbing the whole formation, but here in this it is disturbing the other robots, and that's the benefit of using our proposed algorithm. And now we can go back to the conclusion. Here we can conclude that a formation preservation set point control algorithm based on APF was proposed. The second point is the proposed modifications suppress unnecessary APF induced displacement of the robots that have already reached their target points while retaining attractive repulsive interaction for the robots still in transit. Third one is the Lyapunov analysis established closed loop stability. The fourth one, simulation with 9 robots demonstrated improved formation stability and positional accuracy while maintaining safe inter-robot distances and collision avoidance. And the final point, the proposed method introduced negligible additional computational overhead. Okay, and the takeaway is that the proposed controller improves formation preservation in dense multi-robot system by reducing unwanted motion of converged robots without compromising safety or decentralized operations. Okay, so thank you so much. I hope you have learned so many things about the controls in this video, and you can also develop this controller. If you have any problem, I will put my email ID and also put Dr. Wojciech Kowalczyk email ID on the video description, and you can contact any of us for this. And if you would like to collaborate with, if you have some idea about the controls, of course, we are open to collaborate. Thank you so much. Have a good day. Bye.